The technological advancements of the 21st century have led to the rapid digitization of industry, a phenomenon referred to as Industry 4.0. This union between physical assets and advanced digital technologies is blurring the lines between the physical and digital worlds. Central to Industry 4.0 are technologies such as 5G, advanced robotics, and virtual reality. Most of us have some understanding of what these technologies are capable of in theory, but what tangible impact will adoption of these technologies have on our lives and workplaces? Imagine you could control a robotic avatar, allowing you to remotely explore distant places and even interact with people and the environment around you. What if construction, mining, or industrial workers could use a robot to perform tasks in hazardous environments without needing to place themselves in danger? 5G and virtual reality are making this possible by revolutionizing the field of telerobotics. Hi, my name is Andrew. I'm studying mechatronic engineering. My capstone project is 5G-enabled teleoperation of a mobile manipulator using a virtual reality interface. But before we get into the details, let's have a look at the current state of the project. Telerobotic systems are comprised of three main components: a master system that hosts the control interface, a slave system that contains the robotic resources, and a communication pipeline between the two of them. In this project, the master system consists of the following: a digital twin of the robot, a user interface that allows the operator to interact with the digital twin in 3D space, and a server PC containing high-performance computing resources. This server PC takes requests provided by the operator and performs motion planning, collision checking, and control using MoveIt. The slave is a KUKA KMR IIWA mobile cobot. It is comprised of a mobile base, 7 degree of freedom manipulator, and various RGBD cameras allowing visualization of the robot's environment. This robot takes instructions from the server PC and returns sensor feedback from its robotic arm, mobile base, and RGBD cameras. The communication pipeline is a private 5G network set up at UTS Tech Labs. There are several challenges in the implementation of a telerobotic system. The first is user experience. Telerobotic systems can be very complex, so to be efficient and accessible, their control interfaces need to be as easy to use as possible without limiting functionality. Conventional 2D interfaces, such as touch panels or a monitor, mouse, and keyboard, can't provide the user with an accurate representation of the remote environment and make interaction and manipulation difficult. Immersive virtual reality interfaces provide a natural and intuitive method for teleoperation of mobile robots. Interacting with a robot model and visualizing feedback from sensors in 3D space enables more efficient, dynamic manipulation and instinctive decision-making. This reduces the need for specialized training often required by more esoteric 2D interfaces. To create the VR interface, I began by setting up a network bridge between Unity and the server PC. I then built a digital twin of the robot in Unity using URDF scripts to define the joint relations and physical properties of every component to mimic the real robot. The digital twin communicates with the server PC using ROS communication. I added visualizations of 3D sensor data using software developed by a postgraduate student called RealityStream. This software takes compressed data from the RGBD cameras on the robot and renders 3D point clouds in Unity. To allow the operator to interact with the digital twin, I created virtual hands and a graphical user interface attached to the user's wrist. The operator can use simple grabbing and pointing motions to move the goal marker and select commands on the user interface. I improved user awareness by adding a projection of the robot's workspace and visualization of the planned trajectories generated by MoveIt. These features allow the operator to use intuition to make decisions and anticipate collisions. As a team of UTS researchers were also using the real robot, I did not have frequent access to it. To provide a control and to test my VR interface, I had to create a gazebo simulation hosted on the Edge server to act as a substitute when the real robot was unavailable. This gazebo simulation operates identically to the real robot and provides the same sensory feedback to the operator. The other primary challenge was networking. Network bandwidth and latency are the main handicaps of teleoperation systems. Natural real-time control of a mobile robot through virtual reality requires low latency, high bandwidth communication. At the same time, the ability to visualize the remote environment requires copious sensory data. Previously, this has restricted telerobots to wide communication, which limits range and mobility. Onboard computing is also often needed for intensive control and sensor data processing, increasing robot cost, size, weight, and power consumption. Consequently, speed, mobility, and battery life are compromised. To address these limitations, private 5G communication was used to facilitate real-time VR teleoperation and environment visualization, while also enabling powerful computing resources to be provided wirelessly to the robot. The breakthrough moment in this project was when I realized the utility of 5G for telerobotics is twofold. 5G enables the creation of a mobile telerobot with a robust and efficient wireless virtual reality control interface. It provides this improvement while also enabling the offloading of the robot's computing to the cloud, improving battery life significantly and allowing for a smaller, lighter, cheaper and more efficient telerobot. The key innovations provided by this project are, firstly, the creation of a real-time wireless virtual reality control interface that is more accessible, more capable and more efficient than existing interfaces. Once again, the other is offloading of computing resources, extending battery life and allowing for lighter, cheaper, more mobile, more efficient telerobots. These features differentiate the system from existing telerobotic solutions. As a result, this solution has the potential to have a big impact on a rapidly growing market. A recent report released by researchermarkets.com in July 2022 found that the global teleoperations and telerobotics market is poised to reach approximately $81.9 billion by 2027. Over the same period, cloud robotics as a service use case will increase by over 70% due to teleoperation solutions. Telemaintenance in particular will grow rapidly between 2022 and 2027 globally. The sectors that present the greatest opportunities for telerobotics are mining, defense, construction, manufacturing, farming, emergency services, and remote health. Going forward, I plan to investigate the potential to stream three-dimensional sensor data into the virtual environment, such as LiDARs and 360-degree video. This would further immerse the user, improving their awareness and ability to interact with the remote environment. I would like to thank my supervisors, Dr. Gavin Paul and Eugen Lai, for their support and assistance throughout the projects. I would also like to thank Dr. Mark Carmichael, Tony Lee, Ricardo Canasti, and Sheila Shujupto. Thank you.